So in the next talk, I'm very excited about because we will see a live Knime demo. So I have the pleasure now to introduce Michael Koeppl, who is head of IT and compound management at Hit Discovery in Constance, and he's also live in the studio. Welcome, Michael.
Hello.
Great to have you. So, Michael, you will be talking about cell density, right? Why is measuring cell density something of interest in the lab?
So if you're doing an experimental assay with cells, it's quite important to have the cells at right density because the cells sense a neighborhood of each other, and they may behave completely different if they're sparsely scattered around the area or if they're really quite dense. So the results will be different. And if you do an assay, the results will differ from day to day if you don't take care about the right density. If you do it over days, over months, over weeks, you will get great variation in the results. So it's about increasing the quality and reproducibility of results.
Yeah, that makes absolute sense. And where do you see the advantages of using Knime then in this context?
So either you do it visually or you use some machines for determining cell density. The advantage for me is that it's like a Swiss Army knife which you plug onto your lab devices. So you want to change the system, you want to evaluate something different, you have a lot of things, a lot of nodes in the Knime, let's say, universe which you can use, and so you can iterate, you can agile, try to tune your systems and to get better, and you can do it by your own. So we'll see later in the talk, if you couple these both systems, you're free to, let's say, invent your own analysis and feed them back into the lab.
Cool. I think now we all want to see how to invent our own analysis.
Okay, so in my talk, I will talk about the measurement of cell density with Knime and SiLA for cell culture. More or less, this will be, let's say, the motivation or explanation, what you saw earlier, what Rob presented, and also what Patrick presented. So why we did this, how we did this, and what is the goal. More or less, the complete idea is sketched on this side. What do we have? We have Knime. With Knime, you can analyze and process the data with a lot of nodes and a lot of possibilities in the whole ecosystem of Knime. With SiLA, you have an open standard enabling to interconnect different lab processes and lab data. So the idea is connect those both components and connect Knime to the lab data and the processes and try to make a system out of this. The final goal for me is really the emancipation of laboratory IT. So I think that laboratory IT should be as easily usable and also measurable, combinable as nowadays consumer electronics. So if you use your PC, you plug in your headphones, your camera, you don't care if it's a Mac or if it's a PC, it just works most of the time at least. And the idea is, the final goal is to give the lab people the same freedom in designing their own system as you have the freedom designing your own personal computer. If you talk about laboratory automation, you always have roughly 4 steps. You have to start a measurement. When the measurement is finished, you get the results from the device in a binary form. You have to convert the data most of the time into a format and load it into analysis software, which might be something like Excel or something like this. And the next thing is the scientist decides on the parameters for the next experiment, just to get a better quality or to improve the results of the experiment. If you look into lab, you have 2 very different worlds. So one world is the thing you have in mind if you're looking at sci-fi movies. Cool people in coats running around on machines with a lot of lights and a lot of things. And this is really the case. So we have robotic lines running 24/7 with a lot of robotic arms, a lot of devices, and a lot of software controlling them, integrating them. This is what you see here on the left side. So these are the fully integrated systems. They run very well. They have produce a high quality. They have a high speed. They're also quite costly. And what for me is the problem is they're quite rigid. So if you want to change a simple step or integrate a new device, it's quite difficult. Normally you call the vendor. If you're lucky, you have an engineer at hand and he integrates the system or the device, but it's not that easily to change your experimental setup. On the other side, on the right side, I would call it manual tool chain. You have the same devices as in the fully integrated systems. You have also lab devices, you have data, you have software, etc. But what you have on the right side on the manual tool chain, you interconnect these different parts with human robots. And these human robots are people, biologists running around in the lab, feeding machines, getting data on a USB stick to Excel, analyze it, and then thinking what to do next. Well, you're quite flexible with this. You have at least the invest costs are quite low because you have everything at hand, but you're quite slow and you're also error prone. So the idea is how to combine both worlds, so the best from both sides. So being flexible, but also being able to automate things and not, let's say, being just a servant of machines. The idea is we cannot get rid of the different parts. We have to measure, we have to get the data, we have to analyze the data. So this is just given. But what we can do is just to change the interface. And the proposal that I have, at least for today, is that the interface could be via Knime to control devices, to get data from devices, also to push the data for analysis to some software and integrate all these different parts with Knime in the center as a hub, as an orchestration software. So you can tune, this is the idea, tune your Knime with a few little tricks into an, let's say, scheduling orchestration software where you can control your lab over SiLA with just a few clicks. So you will have high speed as before, if you have a robot somewhere inside. So if you don't have to tell somebody to put your plates from A to B, you will have a better quality, but which is important for me, you're still flexible. So you can design your own workflow. And I think most of you know Knime and know how it works. You drag and drop your nodes, you do a new analysis, and next day your boss comes to you and says, well, can we do this analysis any better? Can you sort out some cells? Can you sort out some data relics? And I say, okay, I do it in my Knime, and then I do the experiment again. So you're quite free to do what you want in an automated way. And also the invest costs here are lower than, let's say, for a full-blown, fully integrated systems. The thing I now show here is the setup that Rob already has shown. So as said before, we want to measure the cell density. In this first sketch here, in the first workflow, we measure nucleus in the first place. And the idea is to connect, as you've seen before, to connect the microscope data to Knime and evaluate the cell density, or at least a number of the cells, directly with the image analysis nodes from Knime. So the microscope images are sent from the microscope to Knime. Knime receives the images over SiLA. We'll show later how this works, counts the cells or the nucleus, and sends this data back to the SiLA server. So when I have this data, either a human robot, again, can decide what to do next, or I have a robot which speaks SiLA, then I can directly plug in this robot that speaks SiLA to my SiLA program that receives the data. And so the robot then can decide, is it okay, or is it not okay? Should I incubate the cells more, or should I measure them directly? You can also integrate it directly, for instance, with Biocero's Green Button Go with a SiLA interface. How does this look like? We have three different layers. Lower layer, this is the lab where really the work happens. Then we have the SiLA layer for interconnecting, and we have the Knime layer to evaluate the data. So on the microscope, we have a small program that gets the pictures in the zip file, sends the pictures in the zip file if Knime requests them to a component, which you can directly download from the internet. This component stores the pictures, unpacks them, stores them locally. You pass the image through to the Knime image processing nodes, and then the result numbers are sent back over a separate component to the same SiLA server, either to a robot or to a human, who then just gets the result. So you get image analysis directly coupled to your device. And if you're lucky, you have a robot, you can automate. Robot decides then, or the human decides, are there enough cells? Are they dense enough? If yes, then I go to the measurement. If no, I put them back in the incubator for 1 day. Important for me is to also show you how it looks, like, say, in the background. So what you have in principle are these Knime components, which you can download directly from the internet, also the complete workflow. And in this case, we have a jar file. A jar file is something like an executable file, like an exe file from Windows, which is one time stored directly on the microscope, and also a copy of this jar file is then in your workflow integrated. So how it is done, the jar file gets called, gets the request to send the data. The jar file in the Knime component hands over this data. The Knime components unpacks it, and the same as jar file takes care about sending it back and to the robot. This is the workflow that also Rob used, developed together with the O'Brien Constance, SiLA, and Knime. I will try to give a live demo of this workflow. You can also download this workflow directly from Knime Hub and play around at your PC. So now I would do the live demo. Good? Okay. Okay. What you see here on top is the Knime GUI as you know it. And here below, I opened up just to Windows where I had to start the jar files, executable files. Reason is I don't have a microscope here at hand, and therefore I had just to mock up the microscope, store a few images locally, and so that I can present it to you. So as I said, this is the workflow that is downloadable directly from the internet. This is the first component who connects to the SiLA server and gets the data. And if I now execute it, you see here on the left lower pane, that the SiLA server receives the request get data. And I told him before, okay, if somebody asks you what to send them the file images.zip, and it sends them back to Knime. You can also here configure this node. So this is running on my local PC, and also I can configure the port, so to say, where I can connect it. So, but it's already done if you download it. So in the next node, in the next component, the pictures are stored, and in the next component, they are handed over to the image reader. If we look now at this, we have two images, quite easy images with nucleus, with cells, with stained nucleus. We have two pictures, and the task is to count the cells or the nucleus which are in the picture. The next node, this is done here in the cell segmentation. So here in the cell segmentation node, all the, let's say, Knime image analysis magic is hidden. And if you look at it, you see here, you're coming up with segmented cells. So every cell is detected, cut it out of the main picture, gets a number to identify it, and also labeled to get a link back to the picture where it comes from. And the rest is just, I would say, pure Knime. You group them together, you make your table, and at the very end, you come up with something like, okay, this picture 8gray.tif, this was the name, has 289 counts, nucleus, cells. And the last part, you send them back to the server, and you see at the server, he gets back, okay, setting variable 8gray. This picture 8gray has 289 counts, and the other picture has 274 counts. And this is more or less the workflow that Rob used that you also can, as said, download from the internet. If I have 1 minute left, is okay? I hope? Okay. I have also received some other pictures directly from a cell culture lab because I have noticed the pictures that you saw will not directly come from a cell flask. And so some friends from Edosia gave us some pictures directly from a microscope, which is integrated into an incubator. It's a CytoSmart system. And the idea is to continuously, in the incubator, monitor the cells to start the process when the cells are ready and not when the robot is ready. So let's have a look at the pictures. So these are the pictures as you would see them just in a normal microscope for cell culture. And you see they are more difficult to detect. And if I would just let the normal image segmentation algorithm run on these pictures, there would be a problem. I integrated just an inverter just to make them inverted so that the algorithm can detect them. So more or less the cells are bright and the background is black. And I just used the same algorithm as done before for the cell nuclei and see what the algorithm does. I should execute it before. No. There it is. So if also here, the cells segmented, not that good for sure. But this is exactly the idea. If you don't like the segmentation here, if you say you can do it better, if you say you want to do it with self-profiler, which I would do normally, or you want to write your own, let's say, AI image analysis, plug it into here, because at the end, all you deliver back is this data here, different pictures, CHO cells, sushi cells, and with data, and you feed them back to your SiLA server. And if you can connect them directly to a robot, you can say, well, do what is needed, bring them back to the incubator, or bring them up to the experiment. Finished now. That's all from my side.
Very cool. Thank you, Michael. I especially like the image of having Knime as orchestration software, because I think usually, right, we think about Knime as analysis software, but here it's really an orchestration software. I like that. So I think we have, that's why you said it, right? We're a little short on time, but I think we should still take at least one question from the audience. Janina, do you have something for us?
Yes, we have a question by Bruno, and he's asking, are users required to interact with the equipment via the Knime workflow, or is it more interactionless thing? And can only key users interact with the workflow?
So if you talk about lab people, the lab people in this scenario, which is, so to say, still a proof of concept scenario, are just interacting at the moment with a Knime workflow. So with a Knime workflow, they click on the, get the pictures, execute it, and that's all they do. Given the case that a microscope is able to connect to the SiLA workflow, for sure. So, but if you are able to connect it to the SiLA server and do your picture automatically, you just click on Knime, and this is the thing I like. So more or less, you sit at your desk and you can really influence the physical world with the data you're analyzing with Knime.
Yeah, cool. Thank you.
Yeah, that's an excellent point. Yeah. And it's fun to watch, right? Very cool. Thank you so much, Michael.